So this is a lecture on randomization in research. It's going to be a long one. If you want to follow along, please do. You can skip ahead however you choose. That's up to you. But let's start talking about randomization. So our goal is to cover, and I'm focusing on the Gordis textbook. Let me just pull that up here. Oops, pull that up for you. Yeah, Gordis Epidemiology. This is chapter 10 and 11, but I'll cover it in my own way. The book is pretty complicated in the way the authors cover these topics. They just kind of throw them at you and they give you these. I mean, this is a great textbook. I've been using it for years through many different permutations, but I'll tell you, sometimes it's just they overcomplicate things when you could do things simpler. So I try my best to simplify it for you, but that's the best I can do. First of all, in order to discuss randomization, we have to talk about different types of experiments. We can divide experiments or experimental designs into strong and weak experimental designs. Strong experimental designs include, well, the the mother of all of them is the randomized control trial. It's the best type. So here the researcher randomly assigns participants to the different levels of the independent variable. So usually we're talking about treatments, or independent variable will be the different levels of the treatment. We'll get into all of that. It's the only method by which the researcher can infer causation. Again, it requires perfect control, and that's what one of the benefits of this design is, that you can control for so many possible confounding variables. To infer causation, the study must have internal validity. So internal validity means that the manipulation of the independent variable is the sole cause of change that we observe in the dependent variable. This is contrasted to external validity. Some people call this ecological validity or generalizability. So the study can generalize to the population as a whole. Internal and external validity are inversely related because to have internal validity, you have to have perfect control of all confounding variables, and it's hard to be realistic because in reality we can't control for all these external factors like, say, temperature, weather, that other environmental and non-environmental factors that can interfere with our ability to infer causation. Just to remind everybody what these are in case you don't know, or if you do know and you haven't seen it in a while, an independent variable is the variable that's manipulated by the researcher. Here's an example of, my famous sunshine pills, right? So we have experimental group receiving high, medium, or low dose sunshine pills. So those would be three different levels of the treatment. And of course, we'd have a placebo as well. And we'll talk about that in a second. And then we have another example would be, in terms of something that's not a drug, it would be something like mindfulness versus cognitive behavioral therapy for the treatment of anxiety, right? You will always have a control group of some sort. For drug trials. The control group is something like a sugar pill, or it could be saline. It's something that's inert, an inert substance. Reason we have it is because we control for expectation, because people do expect something to work when they take it. So there's this nice biological effect of expectation. So it's kind of, that's what we have to control for in these trials, and we want to see if our drug or whatever our treatment is works above and beyond what's expected. In non-drug trials, we usually don't have something known as a placebo. So, for instance, if I'm doing a treatment like like I mentioned here, something like mindfulness versus CBT. Mindfulness may be the treatment that one's assessing. The control would be cognitive behavioral therapy. That's not a placebo. It's just treatment as usual. So we usually do treatment as usual in such cases. Treatment for as usual could be something like I said, cognitive behavioral therapy, or it could be an information pamphlet, or even a waitlist control. Like, you're going to receive the treatment. I think the waitlist control is the most similar to the placebo, because at least you're having this expectation of receiving the treatment. We have to talk about random assignment when we're talking about randomized controlled trials. There are different types of random assignment. There's simple random assignment. So each participant has an equal likelihood of being selected. We talk about selection to the different levels of the treatment. So they have equal probability. Unfortunately, there's no guarantee of equal distribution to the various levels in terms of in number, right? Or in demographic characteristics. Right? So it's important to note that when we talk about not having equal distribution, this means we're recruiting in a sequential fashion. So it's like you come in and then the next person comes in. So you have some kind of method that randomly assigns people to the different levels of the treatment. If I have all the people in advance, like if I have 100 people in advance and I put 50 in the experimental and 50 in the control group, it's really easy for me to control the size of my groups. 50 go here, 50 go here. Even numbers here, odd numbers go there. But especially when we're recruiting sequentially, it's not that easy. In many cases, we do that. I'll talk more about that in a second. Block randomization is one way we can deal with this problem of number. It's a strategy that ensures equal number of participants to the various levels of the treatment or independent variable. We do so we define this is the process by which we do it. We define blocks of participants. Talk about that in a second. I'll show you an example. Block size should be not too large. For like instance, a block could be 4, 6, or 8 participants. You're going to put participants in these blocks, right? Block size must be a multiple of the number of treatment levels. So if we have two treatment levels, like placebo and pill, right? That's two. But either you're going to be in the placebo group or in the pill group. The size should be a multiple of that, like 4 or 6. With a block size of 4, now this is where it gets fun. There are 6 possible block sequences in which participants can be placed in 2 groups, treatment or control. So here's how we actually do this calculation. You may be familiar with this counting rule. You might call it the binomial coefficient, whatever you want to call it, n choose x. So this is what this reads here, 4 choose 2. So I have 4 slots in my block, and I want to put people in the experimental or the control group. So 4 choose 2. How many ways can I arrange those individuals? So this is 4 factorial divided by 2 factorial times 4 minus 2 factorial. Factorial means 4 times 3 times 2 times 1 times 0, where 0 factorial equals 1. Otherwise, we'd have zeros. This gives us 6 possible blocks. All right, so we'll take a look at this here. If we have 8 participants and 6 possible blocks of 4 assignments, right, because their block size is 4, we can assign the first 4 participants to any of the 6 possible arrangements. We can do this at random. Like here's our 8 participants, and here's our 6 possible arrangements, right? We're arranging them at 2 at a time. So treatment, control, control, treatment, control, etc. Right? There's 4 people in a block, right? So with 8 of them, I might put the first 4 people in this block, and then the second 4 people in that block, or whichever way you want to do that. If there are more participants than block, you just recycle the blocks. Weaknesses is that it's easy for the researchers to figure out treatment assignment. By the way, so again, I said I'm covering what's in the textbook, but I'm covering it in my own way. And you see me reading the notes here. These notes are come from my personal research methods textbook. Yes, I can read, but I also wrote all this stuff. I have a textbook of my own that I use to teach research methods. So another way we can deal with issues of randomization is stratified assignment, especially when we have problems with demographic characteristics. And we want to make sure that our assignments are similar in terms of different levels of the treatment in terms of demographics. Like we don't want to have one group that's all male and one group that's all female. Then all of a sudden gender becomes a confounding variable. So we want to be able to eliminate these problems. Yeah, so like I said, we want to get rid of confounding. So confounding means a confounding variable is a variable that competes as a cause for the relation observed between the independent and the dependent variable. The dependent variable being the variable of interest, one that we'd like to see change. So to ensure better allocation across groups, we stratify on a characteristic of interest. and then randomly assign within each level of that characteristic. If we stratify for gender, we could randomly assign within each gender. Boom. If we use block assignment within the strata, we can account for all possible confounds and ensure, well, for possible confounds, not all possible confounds, for possible, like we're doing a block assignment by gender, then we're only controlling for gender. I mean, if we do more than that, then it gets a little bit more interesting because the more the more stratification we use, the more strata we have, the fewer participants we have for each of the categories. Can become a little too complicated. We may run out of participants. So we can do a mix of block assignment and stratification. So you can do whatever you want. There are other methods, and these are, again, apply to sequential recruitment because that's where we have most of the problems in trying to keep a balance, right, between the different or among the different levels of treatment. So, sequential recruitment is, again, you're recruiting people one at a time. I'll give you some examples. Like an experimental surgery, you have to get somebody who has the issue so you can place them in either the surgery or the control condition. An example that a researcher I worked with used was a buffet challenge for people who are struggling from anorexia nervosa. So they put out this buffet. Participant goes to the buffet and they weigh what the person chooses. You get all these different foods. So again, you can only do one participant at a time. You can't like do 100 people at one time. But we acquire participants sequentially, and that's how most of these studies occur because it's not always possible for you to get everybody in advance. Sometimes it is, but not always. One method we can use is something known as adaptive randomization. I really love this, and I've actually used this before. So there's software that recalculates the assignment probability after the allocation of each participant to the treatment level based on key demographic characteristics. You get one participant gets put in the treatment level. If we have this run on all, say, males being put in the treatment level, we don't want to have more males in the treatment level, so we reduce the likelihood of a male being assigned to the treatment. So it increases their probability of being assigned to the control conditions. Really cool. I love statisticians. There are two types of randomized control. Again, this isn't a course in which we're going to do all this stuff. You're learning about this. So I'll stop here. You can always look this up on your own, right? Go into further detail of how to do that. In my textbook, I explain this in more detail. Again, this is epi, so we're not going to go into that much detail here. There's two types of randomized control trials. There's post-test only designs. So you have random assignment to the different levels of the independent variable, assess effect of the treatment on the dependent variable. So only after the treatment. So there's no pretest. One of the strengths is that you have a control group, right? So you can always compare the effect between the treatment and the control group, and you have random assignment, which is good, controls for all these different confounds. Weakness, of course, is you have no pretest to account for existing levels of dependent variable, and you can't test for equivalency on covariates and dependent variable prior to intervention because you want the treatment and the control group to be equivalent on everything except for the treatment, and you can test for that when you have an assessment prior to the administration of the treatment. The pretest, post-test design, this is what we really want to do. You have random assignment to different levels of the independent variable. You assess the effect of treatment on the dependent variable. Perfect, right? Strands, you have a control group, can test for equivalency on covariates, and the dependent variable prior to intervention allows for the assessment of time by treatment interaction, which is really what you want to do, right? It is the change over time resulting from the treatment versus the control, right? So we test that's an interaction. An interaction means moderation. So, right, the effect of time on the whatever the dependent variable will differ between those who are treated and those who are not treatment. So treatment moderates the effect of time on whatever the outcome is. It's the best possible research design. So here's a look at some other weak experimental designs. So Weak experimental designs contrast with strong experimental designs because they lack random assignment. They lack random assignment. Duh. So here's a here's some weak designs. You have the one-shot case study. Well, I'll just look at them, name them one group pre-test, post-test. I'm going to cover them in a second. Interrupted time series, and then you have these non-equivalent designs where you have two different groups, post-test only and pre-test only. This is a lot like what I covered just a moment ago. So in the one-shot case studies, the researcher assesses participants after the event only, cannot control for pretest levels of the dependent variable, and there's no control group. So there's also, so that we have definitely a possible placebo effect and no way to account for other potential confounding variables. Placebo effect is a confounding variable, is a confound. One group pre-test, post-test design. So this is better than the one-shot case design. So you can assess participants prior to the intervention. So this establishes a baseline. One can assess the effect of the intervention by looking for change from baseline. There's no control groups. That's a problem. Important for all designs involving repeated measures. This is actually something that needs to be discussed whenever you have a repeated measure. The spacing, even, and this also comes with these crossover designs, something that I'll mention later. You have spacing between measurements has to be taken into account because otherwise that can influence recall. Like if there's too short spacing between pre and post test, you might recall what you did in a pre-test and that can influence your post-test. If the spacing is too far, you might have change that's not related to the treatment. Okay. So that's introduces a confounding variable. I like this interrupted time series design. So this design, you have something happening, you have the treatment, and then you look at what happens after the treatment. What you want to see is, so this is especially important if you're dealing with younger individuals, because with younger individuals, maturation is going to play a role in the effect. And if we see that a continuing slope being the same from pre to post test versus a change in the slope after the treatment, if we see the same slope, we can say, hey, maturation is the reason why we're seeing this change. However, if we see a displacement of the line, right? The slope is the same, but there's a displacement of the line. I think I said that wrong before. Slope is the same, but you have a displacement of the line. Then we can say, okay, the treatment actually has an effect above and beyond maturation, because it looks like maturation would continue to have an effect anyway. That's an interesting one. A drawback is you have no control groups. A positive is the participants serve as their own controls. Because again, you're the same person, so you're going to change in some ways, but you're not going to change everything about you. In terms of non-equivalent group designs, well, there were two that we looked at here. The benefit is that these groups, we have like a control group, but there's no random assignment, making the groups non-equivalent. That's what they're called, non-equivalent. In the non-equivalent and post-test only design, you have no pre-test. We saw the problems with not having a pre-test. You can't assess change. You can't test for equivalency and all that good stuff. Non-equivalent and pre-test post-design is better, but again, they have no random assignments, so there's no equivalence. A major problem in all research, but we talk about it in terms of experimental designs, particularly weak experimental designs, but pretty much in all designs, because there's something known as selection bias. We try to prevent this by using random assignment to different levels of a variable. In that case, we can control it, but we can't control who decides to participate in a study. Some people are more willing to participate in a study than others, and that introduces selection bias. It's just something you have to deal with. You always put it as a caveat when you describe your studies. Like for instance, if I did digit dialing on cell phones and people who picked up, first of all, not everybody's going to pick up. So some people select to pick up and others don't. So that's already, you have selection bias there. And then if I introduce my study, some people are saying, no, I don't want to have anything to do with it. Others will say, yes, I do. So again, we always have selection bias. People are always selecting to join study. When we're dealing with these non-randomized trials, one of the things we can do is we can match participants, right? So a lot of times it's just not possible. Like if I want to conduct a study on the effects of secondhand smoking on asthma in children, you can't randomly assign people to secondhand smoking for ethical purposes, but we can do some matching. Participants are matched on specific covariates. Covariate is another word for a confounding variable. We just call them covariates, something like income and education. So when we say matching, we actually pick one person in one group and match them to a person in the other group, treating them as if they were the same people in a pre-post test design, right? Treating them like they're the same individuals. They're matched on income, like within $1,000 or something, right? What that does is reduces variability, right? Because you're basically eliminating one of the confounding variable. Of course, one of the problems with that is that you also eliminate that variable as a possible something that you can test too. So there's some problems with it. If you match case by case on selected covariates, it becomes problematic the more variables you try to eliminate or to match people on. It just gets hard to find participants that meet all the criteria, one for the experimental group, one for the control group. But there are other methods that we can use, something like propensity matching. I think this is really cool. You create a discrete, right, like a binary variable, discrete variable to represent treatment assignment. So you have treatment group and control group, right? So that's your variable, and then you do like a logistic regression analysis, right? You calculate the probability of treatment group assignment, so being assigned in group one after a condition on covariates, right? So you match the participants in treatment and control group by a propensity score, some score that gives you the propensity of being placed in the treatment group. That's pretty cool, right? And that's way better than doing matching case by case. Some statistical methods for experimental designs. Ideally, you'd use a mixed ANOVA, or you can have MANOVA if you have more than one dependent variable, but a mixed ANOVA because, well, we have a mixture of repeated measure design, pre to post. And this is thinking about, a nice randomized control trial. You have pre to post test, and then so you have this within effect, which goes from change within the individual from pre to post test, and then you have some kind of a between group effect or right due to the treatment placement, right? So that's really cool. That's one way I would do it. And what we're looking for is an interaction effect. Is there a time by treatment interaction? So that's what we're looking for. And so this is a really good study design for doing this, but it's not the only one. There are other designs. Some weaknesses to this is that it requires a continuous dependent variable. It assumes multivariate normality in terms of the repeated measures, not univariate, not one variable, but multivariate across time. Same variable twice, so that's two dependent variables. If you do it just twice, limited number of independent variables. You can't like have, plethora of independent variables. Well, you never do want that anyway, but you're limited in your number. Difficult to include time varying covariates, variables that are measured at the same time points as the repeated measure dependent variable. So like if a covariate changes over time, I'd like to maybe include that change. I mean, you can do it, but it's not as easy. There are other methods that can deal with that better, including generalized estimating equations. It assesses change in a variable over time. The variable can be continuous or discrete. I love that. One can assess the effect of time varying and time invariant covariates. Yeah, so I can actually pair them. So as I change across time, my predictor and my covariates can change too. We can look at the effect over time. Some weaknesses, it assumes missing data are missing at random. So that available data has no missing values. And if they have missing values, there are a random sample of the missing values are a random sample of the data set. Or excuse me, the data that you have is a random sample of the total data. Um, you have to restructure data depending on, well, you basically have to restructure the data set to long versus wide format. And if you're not sure what that means, you could learn about it if you want to read more. I talk about it in my textbook. but you have to play around with your data to make it fit the use of whatever program you're using. There are other options. Something like growth curve modeling is really good. If you're not familiar with that, you should look it up. Latent growth curve modeling. And this is a structural equation modeling method. I've been working on area under the curve. So area under the curve is just like the area under the curve that's created by the repeated measures. And this is really good if you're not interested in like what's the shape of change over time. It gives you one variable. It's really cool. Let's talk about sample size. So sample size is a big issue when we're designing studies. Unfortunately, my G-Power isn't working on my computer now, and this is some computer I use for work, so I need somebody to upload it for. I'm not allowed to upload things on my own, so I can't fix that right now, but I have pictures here. So when we have to determine the best sample size possible for our studies. That's a big issue. So let's just do some review here. The purpose of sampling, the sample is a subset of elements taken from the population. Could be people, non-human animals, or whatever. It could be widgets. Right? Is that some fictitious thing? The population includes all possible elements with a characteristic of interest based on whatever factors one is interested in. For instance, for people, it could be something like ethnicity, like you take all Hispanics, there's a population of all Hispanics. Education level, all individuals with less than or equal to a high school education, right? That's another population, and so on, right? The population defined by the characteristic of interest is known as the sampling frame. So here's an example, study of depressive symptoms among adults 18 and older with a high school education or less in Pennsylvania. Our sampling frame would be all adults in Pennsylvania, 18 and older with a high school education or less. That's our sampling frame. We collect data from a subset of N. N stands for number of individuals because assessing every individual in the sampling frame is highly unlikely due to time, cost, and access. And that's just hard to get to everybody. Our goal is to make inferences about the population from our sample. So statistics, just I have recall here, but if you didn't take statistics, statistics are sample values representing population parameters. So parameters are these actual population values that we don't have access to unless we're doing something like I don't know, like an SAT test where you have the entire population, then you know what those population parameters are. So one of our important questions is what sample size is big enough for our goal? There's a lot to this. But this is such a fundamental part of research design that it's like it should be more important than anything else you do. So estimating sample size to conduct the quantitative is different from qualitative. Qualitative, you can get away with a smaller, you can do one person, right? A case study. We need to estimate the sample size, how many individuals we need to conduct a study. Again, this comes from my textbook, so when I read this, remember this is me anyway. To estimate sample size, we need power, alpha, and effect size. Power is the probability of rejecting a false null hypothesis. So I'm assuming you know what a null hypothesis is, but I'll go over it in a second. Alpha is the probability of a type 1 error, probability of a false positive result. Hey, it works, but it doesn't. Effect size is a standardized measure of the effect of interest. We can break that down into small, medium, and large. And there's software you can use to calculate sample size. You can also do it by hand for things like t-tests, c-tests, or confidence intervals. But anything more advanced than that requires software. I mean, it's just, unless you like doing it, that's fine. Especially things like structural equation modeling, you really need to run Monte Carlo studies where you do simulations to estimate the sample size and power, etc. Just a quick review of hypothesis testing since we're talking about hypotheses. There's two types of hypotheses, and this is a null hypothesis significance testing. Okay. There's a null and alternative hypothesis. The alternative hypothesis is really our research hypothesis, that hypothesis we wish to find support for. Here's some examples. 3 sets of squats 3 times per week improve ski racing performance as indicated by time down a ski race course. Or exercising 3 times a week for at least 20 minutes per session decreases the risk of type 2 diabetes. The null hypothesis would be the opposite of that. It's the hypothesis we desire to reject or nullify in favor of the alternative, our research hypothesis. So in this case, um, well, I mentioned here null hypothesis significance testing, and we always make the assumption that the null hypothesis is true. And then this is what I'm talking about here, NHST, not a Bayesian type of inference. Conduct studies to see if it is possible to reject the null hypothesis. So our null would be three sets of these are they go along with the alternative hypotheses I had mentioned previously. Three sets of squats 3 times per week does not improve ski racing performance as indicated by time down the race course. I just say it doesn't, right? Exercising 3 times a week for at least 20 minutes per session does not decrease the risk of type 2 diabetes. Okay? There are 4 possible outcomes in hypothesis testing. So we make our decision, and there's this true nature of the null hypothesis. So the null hypothesis can be either true or false, and we can either reject or fail to reject the null hypothesis. So we have these 4 different possibilities. Type 1 error, which is known as alpha, power, confidence, and type 2 error. These two are complements, right? They're complementary. So, for instance, whatever the type 1 error rate is, 1 minus that would be confidence. Whatever the power is, 1 minus power would be beta, type 2 error. So alpha refers to the researcher's acceptable probability of falsely rejecting a true null hypothesis. So you set this in advance. Popular alpha is 0.05, but it's not required. People think that this is written in stone. I don't know how you write in stone, maybe laser or something. An alpha of 0.10 is better for new studies testing novel interventions, studies with low risk to the participant, i.e., nobody can get hurt by a false positive result, and studies that have small sample sizes related to power. An alpha of 0.01 is better when the sample size is large, where you'd have too much power against sample sizes related to power. And a false positive result would harm participants. Like if I'm testing a surgery and I say, oh, the surgery works, but the surgery can kill somebody, we want to make sure that it really, really works before we do it. So we'd set our alpha really low. So let's look at how these are related. Alpha, the null hypothesis, and p-value. These are things that confound students all the time, confuse students all the time. So we'll start with the null population. That's the population defined by the null hypothesis. So we assume that all samples collected belong to the null population. So the null hypothesis will say something, right? The effect is 0. Boom. So here's an example comparing a sample of freshman college students to a population of freshman college students nationwide on happiness. Our hypothesis is that the happiness of our sample is equal to the happiness of the population. So that would be our null population. So there's no difference between our mean sample happiness and the population. The Greek letter means population. And here, the alternative is the one we are interested in, happiness in the sample is greater than happiness in the population. Okay. Note that our alternative hypothesis is directional. Yes, I said it's directional. That means good. And what I mean by directional is I said that our sample mean will be greater than our population mean. So it's indicating a direction. Like in this case, if we look at this this normal distribution here would be on the right side because this is positive. So our sample mean would be greater than the population mean. The p-value is the probability of the standardized difference. When I say standardized difference, right? We, regardless of which one we do, we have to somehow know what the probability is. And the way we do that is by standardizing our test. So we can actually calculate a probability. P-value is the probability of the standardized difference, z-value, for instance. A z-value, if you can't remember, that's a standard, something that's translated from non-standardized into a standard normal distribution with a mean of 0 and a standard deviation of 1. Z-value, the difference between the sample and the population mean or greater, given the null hypothesis is true. So you should remember this. So the p-value represents the probability of the observed difference or greater given the null hypothesis is true. That's what the p-value stands for. Or here, we could ask it as a question, assuming the null population is the true population, what is the probability of our standardized difference or greater? Now, notice here that I don't want to not talk about this figure here. This figure represents the sampling distribution, because when we pick samples, our samples can come from anywhere in the population, right? So this is our population with the population mean. So our null hypothesis is that our sample mean is equal to this. Now, what I mean by equal to it, I don't mean exactly equal to it, but statistically so close that we don't consider it different. The reason that is because we're just picking samples at random, basically, from the population. They could be anywhere. Some samples could have means that are way below the population mean. Some can have means that are way above the population mean. The ones that we consider significantly different are far away from the population mean, not very close. Okay. Alpha defines the cutoff point, the critical value for judging statistical significance. Again, it's a probability, right, of a false positive result, but we have to translate that into a figure. Like, for instance, if our alpha here, I think our alpha here is 0.05, right? Two-tailed, that means it could be, we'll talk about that in a second, either side of the mean. Anything within this purple area here is we're confident belongs to our population. Anything that's outside of these lines, which are defined by our alpha, we're not so confident that they belong to our population. That's how we end up rejecting things. We look for differences that are within these white areas here. And I had mentioned confidence and alpha are complements, right? So 1 minus confidence is alpha. So if my alpha is 0.05, 1 minus 0.05 would be 0.95. So 95% of all values I'd be confident that 95% of all the values within this region belong to this population. So we use alpha to create a cutoff point. So let's work through this here. Assuming a standard normal distribution, and I use this symbolism here because the natural parameters for a normal distribution are the mean and the variance, right? So the mean here is 0 in a standard normal distribution. This is the one we use when we calculate probabilities, right? Mean is 0, standard deviation is 1, and I'm assuming you know what that is, but if you don't, it's something you want to look up. And alpha is 0.05, so we're taking a 5% chance of a false positive result. The z value all z values greater than or equal to 1.645 would result in rejecting the null hypothesis. This is also assuming a one-tailed test. Okay, so what does that mean here? So if we set our alpha at 0.05, that sets a cutoff. And in that example I gave you, I mentioned we're looking at one tail, right? We're saying that happiness in the sample is greater than happiness of the population. I'm not interested in less than. So I'm not interested in this half. I'm only looking at this half. So our 5%, our alpha would be out here, would represent the upper 5% of the distribution, right? And here's the mean. So any value that's further than wherever that cutoff is for 5% would be considered statistically significant because we'd have a probability of value that large or larger being less than 5%, right? Our cutoff here would be 1.645 because this cuts off the upper 5% of the distribution. Yeah, this is cool because a lot of times students say, well, why do we use greater than or equal to the cutoff for significance, but less than or equal to alpha for the significance? Well, that's why, because this is the cutoff point. Things that are above it would be significant, right? But anything above this cutoff would have a smaller probability than our alpha. So that's why you have this seemingly contradictory type of explanation here. Okay. So any difference, so we standardize these differences, like say in the, I think I put the equation here somewhere, maybe. No. Yeah. Oh, no, I don't. But if we were doing a test of some sort, we'd have a score, a z-score. So this z-score would tell me how far away from the population mean we are. So a z-score of 1.645 is pretty far away from the mean, right? It's what's uh, 97.5 divided by 2. Actually, 95 divided by 2. So that's how much further it is away from the mean, right? Again, this is symmetrical, right? This represents 95% of the population. So from here to 1.645 would be half of 95, right? So yeah, 47.5% of the values fall between 0 and here. So that's what this cutoff is, right? 1.645. It's 45%, 47.5% above the mean, right? But it's pretty far away. So anything beyond that we consider as being statistical. Any mean difference. So when we calculate this mean difference, it's the actual difference between our sample mean and the population mean divided by a measure of standard deviation. And when we're doing statistical testing, our standard deviation is something called the standard error of the mean. Again, this isn't a stats course, so I'm not going to go into all that. And hopefully you understand that. If not, you can consult your local stats book or your local statistician. You should consult your local statistician. Okay. So let's see, let's assume that our calculated z-score is 1.96. Okay. It's a standardized difference between the sample and the population mean. Okay. We conclude that our sample has greater happiness than the population mean, so we reject the null hypothesis. So what does that mean? So let's say that our z-score that we calculated based on the difference between our sample and the population mean is 1.964. So it's basically 2, right? That's further away from the mean than our cutoff. So that means it has a lower probability of occurring. In fact, we know that the probability of a value this large or larger is going to be it's going to be less than 0.05, right? It's going to be less than 0.05. Should be 2.5%, right? Because this actually is our critical value for a two-tailed test. So I think 2.5% of all values would be greater than this, right? So just the probability of an observed result this large or larger is going to be 2.5%. If we set our critical value at 1.645 or our alpha at 0.05, we said we'd reject the null hypothesis if we conclude if our probability, our p-value, our probability of our observed result or larger was less than or equal to 0.05. 2.5 is less than or equal to 0.05, so we can reject the null hypothesis that our sample is equally happy as the population. So we have a sample that's happier. Okay. Mm-hmm. So we believe our sample comes from a happier population than a null population. We may be wrong, however, because people, and this is really important, we may be wrong because people may have been excessively happy on the day of testing. Why would people be excessively happy? Well, maybe the football team, this is Philadelphia, so the Eagles might have won a game and everybody's all stoked because of that, or the Phillies won a game or something like that. People are really happy. A key game, and you just so happen to sample on that day. Or if the team lost, people might be really, really sad, right? However, and here's the thing. So we got the z-score that was 1.96. And we know that the probability of a value that large or larger is only 2.5%, right? Right. So we set our alpha that high because we want to account for the possibility of these spurious results, right? These weird results. So we may be wrong in concluding that our sample is happier than the population, again, because it was just a random event, like a football game or something like that. However, this is the important thing. Given the rarity of a difference that large or larger, the probability of being wrong if we make this conclusion is only 2.5%. And we can live with that, right? Especially if we set our alpha at 0.05. So in this way, we account for the possibility of errors. If we were to use a two-tailed versus a one-tailed test, so just to be clear here, when I make a directional null, an alternative hypothesis, I'm assuming like my sample is happier than the population. I benefit from having all of my alpha and one tail I could have said, I could have hypothesized that my sample is less happy than the population, and then that also would have been directional, but all of my alpha would have been on this side of the distribution. If I'm not sure, though, I might say, well, they could be happier or they could be sadder. Right? I'm not really sure. They just differ from the population. That uncertainty, if I want my alpha to remain 5%, has to be split in between these two. The outcome of doing that splitting is that my critical value moves out, right, to 1.964 or negative 1.964. So that's why I chose 1.964 for my example. So what I do is I'm moving the cut point further away from the mean, making it more difficult to reject the null hypothesis. So it's better to do, honestly, it's better to do a one than a two-tailed test. However, if your sample size is large enough, that may not make a difference. Okay. So I would say that you have more power using a one than a two-tailed test. So let's go and look at sample size and power because I talked a lot about sample size. I mentioned increasing the sample size makes everything better, makes life easier. So let's take a look at how that happens. So the standard deviation of the sampling distribution, the mean, is known as the standard error of the mean. Going back to this figure here, if we look at just the means of these samples and we calculate the standard deviation of these means, we'd have the sampling standard error, right? We'd have the standard error. It wouldn't be the standard deviation, it would be standard error because we're adjusting for sample size. We have to account for the sample size, assuming the sample size is equal for all of the samples. And our standard error of the mean is our standard deviation divided by the square root of the sample size. If you want to know how you get that, you can look it up. I think I have a video showing how to do that, so probably. So what happens if we increase sample size? So this is kind of cool. So let's here I'm looking at oh here's the Z Z test. We're comparing a sample to the population, right? But we're using a negative, a one-tailed test. I think it's a one-tailed test, yeah. But where our sample mean is less than the population mean, so it's going to be negative. So imagine our sample mean is below our population mean. As such, our Z value is negative. What happens if we increase the sample size? Well, what that'll do is that'll narrow the the little distribution here. So we're talking about our sample, right? We're assuming that our sample is its own population, and we're collecting samples from that population here, right? When we increase our sample size, say from 20 to 30, well, in order to reject the null hypothesis, our sample means have to be further away from the population than the population mean itself from zero, right? And we have this cutoff. In this case, our cutoff is z of negative 1.68. So we're doing this, I said 1.6. I should have been 1.645. That was a typo, which I got to fix. So this is like cutting the lower 5% of the distribution, right? As the sample size increases, just due to the nature of this quotient here, it's in the denominator, our standard error will decrease. Our standard deviation remains constant, right? This is the population standard deviation, remains constant, but the sample size increases. So you see the standard error decreases. What that does is it narrows this normal distribution, and more of this is the cool part, more of it is to the left of the critical value, right? So if you imagine this itself being a population, you're collecting tons of samples from this. Any sample in here would fail to reject the null, right? Even if you have a true difference. So that would be your beta, your type 2 error. Any sample coming from this region here, the area under the curve here, would reject the null. By increasing the sample size, a greater proportion is beyond, right, the cutoff. Isn't that cool? That's why, my friends, especially those little cute Christmas stories, that's why Santa has a beard. Well, that's why we having a large sample size will result in more power. Okay, so that's really cool. Yeah, very, very nice. I don't really need to talk about any more of that. Effect size is a standardized measure of practical significance. I mean, we try to standardize things. I mean, we talk about something being statistically significant. It may be significant because of sample size, right? So there's also a problem when you have a large sample size. We'll say, it's well, if you have a large sample size, basically even a minor difference can become significant, but that doesn't mean it's practically significant. So we ask clinicians, what's a practical level of significance? What's a significant change, significant difference? We try to standardize those because statisticians are always trying to standardize something, right? The two widely used, and there's so many different types of effect sizes depending on what statistic you're using. Cohen's d is a standardized difference between groups. Like if you have control and experimental group, you can standardize the difference. Values between 0 and zero point 0.2 and zero point 0.5 are small, and then you have medium and large, values greater than or equal to zero point 0.8. Correlation coefficients are an effect size. Okay. And you have their heuristics here, right? So larger correlations are better. You can use G-Power. I mentioned this earlier, a statistical tool you can download for free and calculate sample size. There's so many different types of analyses you can do. Here's just an example. Okay. But in order to do that, you need certain information. So a researcher is interested in studying happiness in traditional college students ages 18 to 22. The results of recent studies suggest that the population mean on happiness among traditional college students is 170. It's an estimate. What sample size would we need to detect a difference of 20 points, assuming that there is a sample of very happy individuals scoring 190 and a standard deviation of 40? So we have certain data that we need. We select a one-tail test and an alpha of 0.05. Again, that can vary. We also selected a medium effect size. So that's what we believe the effect size will be. You need something to back that up. In a research design, you have to back up your effect size. But why wouldn't I pick a large effect size? That would be the best, but you need a lot of data to back that up. And for power, probability of rejecting a false null hypothesis, the standard is use 0.80, 80% chance. You don't want to use 100% because then you're going to be overpowered. And you certainly don't want to go really low either. Here's our output from G power, showing where our alpha is and our beta based on that specific sample size, right? So this is kind of like what I showed you when we did that shrinking distribution. So complement of power is beta, complement of alpha is confidence. This is one tail, so it shows you here our effect size Cohen's d is 0.5. You can actually ask it to determine it. So if you click the determine button, you get this little window here. So I plugged in mean of 170 for the null. Alternative was 190, and my standard deviation was 40. Gave me an effect size of 0.5, which it populates this little window here. And I put in the alpha and I put in my power, and it tells me, oh, I need 27 participants to run this study. So it tells you total sample size and what the actual power would be with that sample size. It'd be like 0.81. Pretty cool, huh? You can also print out something like this that shows you what's the effect with different number of individuals based on this. So we had power of 0.8, we had 27, that's right here. But what happens if I go to 35? And so see my power increases, right? Pretty cool. If we did a two-tail test instead, I would need 34. So I lose some power by doing a two-tail test, right? Because I have to split my alpha. See, alpha divided by 2, split it in half, right? So that changed where my critical value is. This was using a t-test, right? We were comparing a sample to a population, where we didn't have a population standard deviation. We just used our estimated one. So you can see there's a difference from the one to the two-tail alpha, right? Okay. Yeah, so that's interesting. So you can do whatever you want. Some other issues that I want to deal with before I finish this nice lecture here. In these studies, we often have what is called unplanned crossover. So you have people assign, let's assume we have just two groups, experimental experimental group and control group. Sometimes people cross over, people who were in the experimental group go into the control group for whatever reason, right? participants change treatments for whatever. Maybe they don't like the treatment, they're scared, and they want to jump into the control group, or oh no, I want to be in the experimental group because I learned that maybe you have a terrible disease, and I've known people who've had loved ones with terrible disease, and they do whatever it takes to be in the experimental rather than the control group because they just want to save them. But it can have an effect on the results of the study in terms of type 1 error, type 2 error. So depending on which way the winds are blowing, the best solution is to use what's called an intent to treat analysis. So you analyze participants as they were randomly assigned despite of the treatment received, right? So somebody who was in the control group, even if they go into the treatment group, they'll still be treated as being in the control group, right? So what that would mean is if they have a positive effect of the treatment, that'll shrink the difference in the statistical test between the control and the experimental group, so make it less likely to reject the null. So that's a must. You don't want to do treatment as received. You don't want to analyze it that way. We also have issues of compliance. People don't always comply with the treatment they were assigned. There are so in the Gordis text, four different types of non-compliant or compliance were discussed. There's the what, and this wasn't actually from the Gordis. He may have done this too. Honestly, I picked out an article and I just was reading about it. Um, I haven't done as much of this type of research myself, right? So this wasn't in my textbook, but I think in the next revision I'll put it in there. So there's four types of compliance issues. There's always takers, always take the treatment regardless of the assignment. So you think about it, people who you have an aspirin study for heart disease. Some people will always take aspirin, regardless of whether you tell them, hey, while you're in here, don't take aspirin, but they're always taking it. Never takers, people who never take the treatment regardless of assignment. The only ones not taking the treatment should be in the control group. There's compliers, they comply, they follow the assigned protocol, they take the treatment if they're in a treatment group, they don't take it if they're in the control group, and then there's defiers, the rebels, right? Rebel without a clue. Never take the treatment regardless of assignment. The problem with non-compliance is it decreases the effect between treatment and placebo, increasing the likelihood of a type 2 error. That's failure to reject a significant difference, a difference that you should reject. There are statistical methods to deal with this. I know M plus, one of in structural equation modeling, there's a way to deal with non-compliance. So that's something that I've never done personally, but it's interesting. In terms of looking at randomized, that's my bird, my parrot. Piper is mad about something. Think somebody's taking out trash. So how do we express the results of randomized trials? So one of the issues is to quantify efficacy. So efficacy means the study does what it was designed to study. By the way, efficacy and effectiveness are different, and people confuse those all the time. Efficacy has to do with whether or not it works. Effectiveness is, does it work in a real life circumstance? Like, are people following, complying, and stuff? So with efficacy, we can actually, in a randomized controlled trial, we can look at the rate of whatever in the untreated group versus the rate in the treated group. So if we're looking at a disease, we expect the rate to be higher in the untreated, the control group, than it is in the treated group. So we divide it by the rate in the untreated group. Here's an example. In a randomized controlled trial of sunshine pills for the prevention of the common cold, the rate of infection among participants in the control group was 57%. Okay. Whereas it was 13% among participants receiving sunshine pills, because it always works. Sunshine pills rock. The efficacy is 0.57 minus 0.13 divided by 0.57 or 0.772. So that's a 77% reduction in risk of infection among those consuming sunshine pills, or 772 per 1,000 population in terms if we were doing rate with this rate base of 1,000. We often express things like that per 1,000 individuals. We can also look at the number needing treatment to prevent one adverse outcome, or NNT. That's a cool measure, right? How many people need to be treated in order to prevent a death or to prevent somebody being afflicted with a disease? So that's 1 divided by the rate in the untreated group minus the rate in the treated group. Here's an example. Researchers at Habibara Pharmaceuticals, it's my fictitious pharmaceutical company, tested the efficacy of sunshine pills in the treatment of disease D, a debilitating disease that leaves patients unable to function without plushies. Well, I think there's a lot of this going on right now. So we call this disorder plushyitis. I mean, I see people having plushies everywhere. In a placebo-controlled trial, the rate of plushyitis was 24% among the placebo controls, but only 16% among participants receiving sunshine pills. So if we do the math, we get 12.5, and we round up, right, to 13. We round up to, always round up. Thus, we need 13 treated patients to reduce the incidence being a new case, incidence of plushyitis. Oh, plushy it is a plushyitis by 1. So there we have it, my friends. That was a long arse lecture, but it was worth the time. It was worth it for me. Thank you very much. Have a wonderful rest of the day.